Hello and welcome to this video on conditional probability using tree diagrams and two-way tables. So for starters, we're in this situation talking about a tuberculosis test, which is a transmissible kind of infectious skin disease. The most common way you might have heard of it is if you are going to be living in a dormitory at a college, you normally would have to get a TB test before arriving on campus so that to make sure that you may not put your fellow classmates at risk. And it's pretty applicable to our world today. So in the tree diagram you see in front of us right now, which I advise pausing the video here and copying it into your notes, since we're going to be looking at some of the bottom questions based on that tree diagram. So go ahead and pause it and copy just this tree diagram up at the top down into your notes. And this is for 1,000 people. So for starters, we could say, well, we only have two options for the beginning of this tree diagram. Either they have TB at the beginning, 380 people, or they do not have TB at the beginning, so that's 620 people. So if I were to just write some basic probabilities to start with, probability of a randomly selected patient having TB, in this case, would be 380 over 1,000, which if we reduce to a percentage would be 38%. And then the opposite, the probability of not having TB, that is what is known as a complement probability, where it's just the probability of it not happening, or just 1 minus the probability of it happening. In this case, we have only 620 people left for our only other option for this, and that would be 62% of people. So we have two basic probabilities happening so far. So now what this is going to be all about is something known as a conditional probability. So that is going to be our main idea. And that's what you see down here, conditional probability notation. So off to the side, what a conditional probability basically is the probability of an event happening given that a first event has already occurred. What I'm basically saying is that we have event A happens in the past. We know it already happened. And then given that we know that A already happened, what's the chances of B happening? In general, we are basically saying that the probability of B given A, like that. So that would be the same as saying the probability of event B given that event A has already occurred. Now, these conditional probabilities will be a big focus of Math 2, and that this is building on all the probability use topics you covered in prior grades. So for starters, we can find two probabilities they're asking about. So in these two situations here, we have number of patients who test negative given that they have TB. Well, that's not a great thing to have happen. This is what is known in the medical community as having a false negative. It means you have the disease, but once you're tested for it, it comes back as negative, even though you're not actually negative for that disease, which is an issue. So how I'd write this out and figure it out is that I basically want to write it as the probability of a negative test given that little vertical line that the person has TB. So the easy way to think about the conditional probabilities is they're kind of we're making a fraction inside of this probability statement here. So we're basically looking at the total number of TB patients would be the denominator if this was kind of a sideways fraction, and the number of negative tests out of those people would be the numerator. So number of negative tests out of the TB patients. So if we look at our tree diagram, we have that negative given TB, tested negative given TB is this number right here. There are 19 people out of the 1,000 basically that have tested negative given that they had TB. Total, 19 people who tested negative in this situation. So if we know that the person has TB, that is 380 people. That would be our denominator. And then given that we know that we're picking out of those 380 people, 19 of them end up having a negative test. So if we did 19 divided by 380 people, we would get exactly 0.05 or 5%. So we have a 5% chance that we test negative if we are a TB patient. So we're basically saying that a false negative, it has a 5% chance of happening given this whole scenario. So the next situation, the number of patients who test positive given that they do not have TB. This in the medical community is known as a false positive. You test positive, but you don't actually have TB. So if we want to look at where this number is, so testing positive, we would write as testing positive given that we do not have TB. We would have you write it. So we need to put the number of no TB people in the denominator. That's 620 people who did not have TB. And then out of those people who did not have TB, the people who are testing positive is 62. So if we do 62 divided by 620, well, that should be an easy one to figure out percentage-wise. But if you weren't sure, that ends up being 0.1 or a 10% chance of a false positive. So it's a greater chance that you have a false positive than you would have a false negative, which neither situation is great, as you might guess, but it's actually a better situation, and it's better to have more people who are getting false positives than false negatives. In this situation, if you have a false positive, well, that means you're going to be more cautious. You're going to seek medical help from a doctor or a medical professional and do more testing from there. But if you go through a test and you have the disease, but you test negative, well, that might give you a false sense of security or might not prompt you to seek further medical help. And that would be a more dangerous thing to have occurred. And that is how you find some basics of conditional probability. So to do a couple more examples here. So we already found number 6 there. So if we can adjust our camera here, you can see some more of our practice problems. So we already did number 6 and number 7. We just found false positives and false negatives. So if I wanted to do number 2, find the probability of testing negative given that you have TB, well, that's actually the same we just found. So these are kind of the same sort of ideas. Sometimes the false positive is that's kind of the wording version of that. So that's kind of the same probabilities. So now, if you were to look for some other ones here, like you could find other examples of conditional probabilities. Like I could find the probability that the test, we can move on. So the probability of a test being correct. So we can think about the two situations where that could be correct. So one situation that would be we have TB and then we test positive. So let's kind of look at that individually. So we'd be finding, I guess, the probability of a positive test given that we have TB. Well, that's a good situation. We want to know that we're positive if we actually have a disease. So now if we look at the people who have TB is 380, and then we have the people who test positive out of those 380 is 361. And if you did that in your calculator, you would have, that's 95% chance to have happened. positive given that you have TB. So if we go the other direction, if we have the people who are testing negative, given that they do not have TB, well, that's good. You don't have the disease, you test negative, and you're able to move on. So now if we look at no TB, that's 620 people. And then if we are looking at the people who test negative, that would be the people who test negative is 558 people. So that percentage, so 558 divided by 620, well, that would be a 90% chance, and then 95% chance. So those are pretty high percentages for accurate testing in either direction that you follow. So if we are looking at moving to a different form of this sort of situation, so we can move on to now what would be a different sort of diagram. So here we have what is known as a two-way table. So you can see that we have rearranged our numbers. So we have the 1,000 total people. That is our sample space. We're choosing out of 1,000 people. So now if we look at different events that could happen, well, we have events, well, you could have TB or you could not have TB. You could test positive and test negative. Those are two events. And you can find totals very easily of all this stuff happening. So there are 380 people who have TB, 620 who don't. We had 423 positive tests, 677 negative tests. So if we are looking at some of these situations, well, if we wanted to find some of these same answers from before, we have 361 people who are testing positive for TB. So the TB 361 out of 423 people, that would be a correct test. We have people who have TB given that they have tested positive. So if we divide those, 361 divided by 423, you get 0.85 or 85% chance of selecting somebody who has TB given that they are a positive test. So one interesting way to look at this is that you could rearrange these two also. So if I was looking for people who test positive given that they have TB, so the people who have TB is 380, and then I would just look at 361 out of that 380 would be positive tests out of the TB patients. So then you would just do 361 divided by 380, and that would be a correct test. And so we have 95% of those to find that answer. So many students typically find the two-way table is easier to do for conditional probabilities because, like, if you're doing like the one we just did, if I know I'm choosing out of the TB patients, I could just do 361 out of 380, and I kind of have everything kind of in one column together. For the first one, since that was positive test, those are in one row together. So you just need to do 361 divided by 423. And so that means that you have everything kind of lined up ready for you to use them in whatever problem you're working on. So if we are looking at number 6, so number 6 says, based on the probability statements from the tree diagram, what would you say to a friend regarding the validity of their results if they are testing for TB using a skin test and the result came back positive? So we know that the probability of testing positive is 423 people out of all 1,000 people. So we would have a 42.3% chance that these people are testing positive. And that just includes the idea that you could test positive without actually having TB. And we talked about that earlier with a false positive. And that is kind of within that percentage chance. So generally speaking, we have 1,000 people in this sample space. And if you kind of think about how you might think about polls, usually 1,000 trials or 1,000 people is usually a kind of baseline for large medical studies or large polling studies. We want, in general, the scientists are doing the testing to figure out how accurate a test is for a certain disease. They need to see if this will work or not work, depending on what kind of testing that they're doing. And we want to make people are comfortable with the results that they get. So the idea that we talked about previously is that we want to have the theoretical probability, the test designed a certain way to catch a certain amount of these positive tests. And we want that to be as close as possible to our experimental probability. Well, the experiment would be us actually collecting the data and looking at the results, and we'd be comparing it to what we expect from this situation and this test. And that shows now what conditional probability is within this example. And we could use a tree diagram and a two-way table to make that happen. And that covers this section of our chapter. Thank you for watching.